So like Jen said, we're going to talk about some biological aspects of how our minds create or discover, especially the discovery part of mathematics. Yeah, usually I do the middle one. Yeah, that good? So we're going to talk about a few things. We're going to talk about some studies that they've done in findings on innate number sense, not just with small children, but also with animals. Connections between language and mathematics, some interesting connections about how the language that we speak and how that relates to our performance in mathematics. We're going to talk about some of the parts of the brain involved in estimation and computation, and then the implications that this has on how we learn math and especially how we teach math. So, for a long time, and actually currently a lot of our schooling has been based on Piaget's theory of how children learn. He believed that children were born without any innate sense of arithmetic, that all of this was learned through observation and imitation, and until age 4 or 5, children didn't really have any concept of number. And what he did is he gave them what he called a number conservation test, and I'm going to show you that in just a second. And until age 4 or 5, they failed this conservation test. So what they would do is he used bottles or glasses, but I just used circles up here, is he would ask children, which is more? Obviously, the bottom row has more, but here they're lined up, and so you can see that the bottom row is longer than the top row, and so when asked which is more, most children would, say the bottom row around age 4 or 5. Then in his studies, what he did is the researcher would then expand the top row to make it longer than the bottom row, using the same objects and the researcher doing it his or herself, and then say, okay, now which is longer? And most often, children would pick the top row. Well, they recreated these studies, a number of researchers recreated these studies, but they modified it slightly to see if children really couldn't understand conservation of number despite row length. So with 2-year-olds, they succeeded perfectly at this test when they were asked which is more. They used M&Ms, they used marbles, and it didn't matter if the researcher moved them or, in a second we'll talk about, they had a teddy bear move them. And it didn't matter, 2-year-olds always got this right, but suddenly when they were 3 and 4, they failed this test. And so the belief is that there was something about the way in which the researcher was asking the question, the language there confused the children. So then they did it again with 3 and 4-year-olds, this time using M&Ms, and they were automatically allowed to pick whichever row they wanted. And so again, with them matching up and then spreading them out so one was longer. And once they were given M&Ms, they always chose the row that had more, even if it was the shorter row. And then another interesting thing with marbles, they had a teddy bear come in when the researcher wasn't looking, and they had the teddy bear move the marbles. And then the researcher would turn around and say, okay, what happened here? So now which is longer, or which one has more? And then the children picked the correct row that actually had the greater number. So the belief is, again, that something about the language, or they misunderstood the researcher's intentions when Piaget did the number conservation test. They've also done some interesting studies with young children. They've actually done studies up to about 4 weeks old. But in one study with 5-month-old babies, what they would do is they would show one Mickey Mouse or one toy, and then they would show a second toy, and then they would put up a screen, and then they would drop the screen down, and if there was just one there, babies looked 1 second longer. So they concluded that babies could understand. They were confused by this. There was 1 plus 1, and then all of a sudden there's 1. That can't equal 1. So they would look 1 second longer at that than when it was 1 plus 1 and there were 2 there. The interesting thing about this is it was also similar with subtraction. So if they started with 2 and the baby saw them take 1 away, And then when they put the screen up and dropped it back down, all of a sudden there were 2 there again. They looked longer at this because there shouldn't be 2 there. But probably the most interesting thing about that is they weren't surprised by what we call magical transformations. So if suddenly Mickey Mouse became a ball, that didn't bother them. As long as the correct number that they expected was there, the time that they looked at it was similar to the correct addition problem. So it didn't matter if it changed form, as long as the number was what they were expecting. Once they got into numbers larger than 4 or larger than 3, and we're going to talk about this more, this is kind of a common theme. Once it was 4 objects, 5 objects, 6 objects, it was harder for them to differentiate. When they did a test with 15-month-olds, they would ask them to pick the larger set of toys, and there was no correlation. It didn't seem like they understood which one was larger, but using a similar test to what they did with babies, they innately understood that if you have one object and another object, there should be 2 there. So while they couldn't understand that 5 is bigger than 4, if you said pick a pile of toys, they would just randomly pick a pile of toys. They could understand that if you had 2 objects, there should remain 2 objects. So what they've concluded from this is there is a link between discrete physical objects and the numerical information. And this actually ends up presenting problems later on when we get into more abstract ideas, because we're so linked to that mental model of a discrete physical object and counting. And this is one example. Once a child learns how to count, they can't help but count every object as 1. And so they did this with a picture of forks in some cases. And so this is an example. Here we can see that this is one whole object that's been broken into 2 pieces. But a young child can't help but count this as 3 separate pieces because they have a 1-to-1 correspondence when they're counting, and they can't see that that together makes one whole. And so that association between discrete physical objects is and our association with it is playing a role there. So I mentioned 1, 2, and 3 earlier, and they've also replicated similar studies, not just with humans, but also with birds, with rats, with chimpanzees, being able to tell the difference between 1, 2, and 3 and greater numbers. So when they were doing this with humans, they would just present flashcards with a number of dots on them. And there was pretty much unfailing precision when it was just 1, 2, or 3. They could do this rapidly, and they always got the correct answer. All of a sudden, once we get into numbers 4 and larger, it's harder for our minds to differentiate between 5 and 6. And so there was actually a linear increase in time. It took more time to answer the question if it was larger than 3 to say, oh, that's 4 dots, oh, that's 5. And the number of errors also increased. So initially they thought, well, maybe it's because if you have 1, it's just a point, 2 make a line, and then 3 would make a triangle. So they went back and they redid all of these tests, changing the orientation of the dots, and it didn't matter. As long as it was 1, 2, or 3, they could answer in a much faster time than anything greater than 3. So this also ties into many of our numbering systems. I'm going to give you a few examples, but many of our numbering systems, once we get past 3, the way in which they've written the numbers changes, and we're going to talk about this with Roman numerals too. And we do this with tally marks. When we make tally marks, every 5th one we cross it out, because if we were to just make a bunch of tally marks with no other system, it's hard for us to look at it and differentiate how many there are. So you'll notice here in ancient Indian, once we get past 3, they've changed the way that they're making the numbers. And the same thing happens this is Chinese. So 1, 2, and 3 are similar, and then once we get to 4, it changes, and also with Roman numerals. Okay, once we get to 4, now we've added in the V here to make it easier to look at it. Because if we had a Roman numeral that was just 4 like this, it would be harder to differentiate it from 3. Another thing about numerosity is that we can more easily distinguish between 2 distant numbers than ones that are closer. So again, they did studies, and they would give flashcards, or they would give 2 numbers, and they would say which one's greater. And it was harder for people if the numbers were closer together. So it was harder if it was a 4 and a 6 versus a 1 and a 9. If it was a 1 and a 9, it was easier, people could answer faster, and they were more likely correct than if it was a 4 and a 6. So the closer numbers are together, the harder it is for our mind to differentiate between the two. Also, for an equal distance, 10 and 20 and 90 and 100, it's harder for our minds to differentiate that 90 is smaller than 100 versus 10 being smaller than 20. The larger the number, the more our mind has to work to understand it. And another thing that they found is that both of these circles contain the same number of dots. But when we look at them, most people would assume that this one has more because they're closer together, because they're more compact. So when we see things that are more spread out, we assume that it's a smaller number than things that are closer together. So the idea is that when we see a digit, we automatically associate it with a quantity in our minds. So the quantitative representation is retrieved, which is what leads to greater confusion when the numbers get larger. We have quantities that are large, and if they're close together, it makes it more difficult. So this is what I was talking about before with it being harder to differentiate between 4 and 6 than 1 and 9. They also, what they did is they gave them, they trained people. They said, okay, we're going to spend 20 hours just practicing with only the numbers 1, 4, 6, and 9. And we're just going to practice, and we're just going to drill you on which is larger, which is smaller. And even after the 20 hours, the results were no different than they were before the 20 hours. They still got it wrong more often when it was 4 and 6 than when it was 1 and 9. So this leads researchers to believe that the way that we represent numbers on a number line in our minds is more like the logarithmic scale on a slide rule, where we compress larger numbers on the number scale together. So while normally when we have a ruler there's an equal distance between 1 and 2 and 2 and 3, in our minds, just like on the scale, the distances between larger numbers, between let's say 1 and 2, is the same as between 4 and 6, which doesn't actually represent the same numerical distance. So we tend to compress these larger numbers all together, which is what makes it harder for us to differentiate between them. Okay, so a quick quiz for you. I'm going to give you about 5 seconds to take a look at Series A and Series B and decide which series is more evenly and randomly spread out. All right, that's all the time you get. Okay, so we'll go back and look at it in just a second. Most people say that Series B is more evenly and randomly spread out. And the reason is Series A contains a lot of large numbers. And so we associate larger numbers because our mind has a harder time processing them. We think that it can't be Series A, when in fact it is. if you were to order the numbers from series A, they were actually an average distance about 200 numbers apart, whereas series B, they were less random.
Does this continue on past childhood? I mean, even today, looking at those, I would
Yes.
guess B. Okay.
Yes. And we're going to talk about kind of the way in which the brain develops and how some of these things don't change.
Okay.
So this is going to also tie into language, but they had a group of people that they were studying, and they had college students doing this in this study. They had adults and they had children, and they had them compare numbers with the number 65. So there were two groups. Group A, if the number was larger than 65, they had to press the right key on a computer. And if it was smaller, they had to press the left key. The other group, Group B, had the opposite. If the number was larger than 65, they had to press the left key. And if the number was smaller, they had to press the right key. So the results of this, as you can probably imagine, Group A responded faster and they made fewer errors. And this has to do with the way we associate the number line in our minds, the way that when we imagine a number line, we always imagine the larger number to the left and the smaller number to the right. And so they did it both with the larger and the smaller numbers. They even had them cross hands and say, okay, just sit where you are, cross your hands, and if it's larger number, we still want you to press the right key, and if it's smaller, we still want you to press the left key, and the results were the same. It didn't matter if they crossed hands, it was the orientation of which key they were pressing. And so they then took students from another country that had been taught to read right to left, whereas we read left to right, and the results were the opposite. So if they were taught to read right to left, then they were better when it was left hand larger, right hand smaller. And so there's a good association between how we learn to read and how we associate numbers in our mind. They've also discovered that children have some unlearned principles of counting that they pick up either through imitation or just learning, watching other people, but not through direct instruction, without anybody saying, this is how you count and this is the way that you do it. They tested 3-year-olds who were unable to count, and they had somebody go through and count. And they noticed when they didn't count in the right order. They noticed when they skipped an object or they counted twice. So if they said 1, 2, 5, 4, 6, the 3.5-year-olds were like, wait, no, you're doing that wrong. Or if they counted an object twice, they said, okay, stop. Even though they themselves couldn't count, they noticed that there were these rules you had to follow when you were counting. The belief is that they don't really appreciate the meaning of counting until the end of the 4th year. So they would say, okay, how many toys did you have? And they found they would just give a random number, 6. Or they would say, give me 5 toys, and they would just give them a big group of toys. So they didn't understand what they were doing when they were counting, but they knew that there were these rules when somebody was counting that they needed to follow. We also have evidence of innate arithmetic. A lot of 6- and 7-year-olds develop their own strategies for addition and subtraction without ever having any explicit teaching. The majority of these are based on counting. We're going to talk about a couple of them in a second. But they come up with these strategies without ever being taught, and they learn quickly to pick the best and most efficient strategy. And so it usually starts with addition, and usually they use their fingers. If I have to do 4 plus 6, I'm going to count 1, 2, 3, 4, and then I have to add, sorry, I meant to say 4 plus 2, and then I'm going to add 1, 2 to that, and then they would go back and they would count, okay, that's 6. And they do the same thing with subtraction. Eventually, they discover that there's shortcuts to that. Okay, instead of counting out 4, I can just start at 4. I can just put up 4 fingers. And then I can say, okay, 5, 6. And they do the same thing with subtraction. So between 4 and 7, they have this innate understanding, this intuitive understanding of addition and subtraction, without anyone saying you have to know that 4 minus 1 is 3. They use their fingers, which actually is a good precursor to students understanding base 10. They understand that they can use their fingers and sometimes their toes to figure those things out. Automatic calculation. We're going to look at this in a second. Once we learn how to add, when we are randomly shown 2 numbers, our mind can't help but find the sum. We just automatically find the sum of those 2 numbers. So what they did in a study is that they would hold up 2 numbers quickly for people to look at, and then they would put them down, and they would ask them if the number they were saying was in one of the 2 numbers they were shown. And they didn't necessarily get it wrong, but it took people longer. If they were shown 3 and 7 and they said, okay, was 10 one of those numbers? It took them longer to decide that 10 wasn't one of the numbers than if they had said 5, because our minds automatically start adding the numbers together once we see them. So we're going to do another quick quiz. This is going to be fast, okay? It's not hard, but it's going to be fast. All right? Okay, quickly add the numbers together in your head. 5, 4, 3, 2, 1. Okay, now pick a number between 12 and 5. How many of you picked 7? Just 2 of you? Then you have to raise your hand. I said, how many of you picked 7? Okay? If you picked 7, please raise your hands. So 2 things about that. Because our minds automatically, we were doing automatic addition, so the opposite of that is subtraction, but the reason your mind was prompted to do subtraction was the order in which those numbers were presented. I didn't say between 5 and 12. I said between 12 and 5. And so automatically, without thinking, you just subtract. So those are some of the things that they found to be innate. And now we're going to talk about some more. We talked about reading, but now we're going to talk about connections between language, words, and math. So I'm not going to have you do this, but if I asked you to memorize this list of numbers and I gave you 20 seconds to go over it in your mind, if you speak English, you only have about a 50% chance of remembering the entire list. But if you speak Chinese, if that's your first language, then you have a much higher chance of remembering all of the numbers on that list. The reason is that when we remember the words. And so in Chinese, the words actually have fewer syllables. And so it's easier for us to recall when there are less syllables because we have less mental things that we're repeating in our mind. Another interesting thing, again relating English language to Chinese, is just how we name the numbers themselves. So we have 1 through 10, which if your language is English, you have to learn through rote memorization. You just have to learn 1 through 10. But also, you have to memorize 1 through 19, because the way in which the words are said, the way in which they're spelled and written, there's no pattern there. And then also you have to learn the tens places from 20 to 90. So by age 4, most kids can count up to 15 successfully. Now in Chinese, there's less rote memorization because there's a pattern. So once you learn the numbers up through 10, when you learn 11, it's just 10, 1, and 20 is 2, 10, and then 21 would be 2, 10, 1. So there's a pattern that they can follow all the way for every number after 10. So by age 4, most speakers of Chinese can count up to 40 instead of 15. They also have an easier time understanding place value in base 10. So what they did is they took children who spoke English and they took children who spoke Chinese and they gave them, you guys are familiar with base 10 blocks. So they had the little blocks of 5, they had the strips of 10, and they asked them to make 25. Well, the children who spoke Chinese quickly grabbed 2 10s and 5 1s, while the children who spoke Chinese counted out 25 1 squares. Okay? So this provides a better understanding of base 10. On top of that, Chinese are far better at multiplication tables, but like we were talking about before, it's less syllables for them to say. And so when we're trying to remember 7 times 8 is, they have less syllables that they have to say, and so it's easier for them to remember that 7 times 8 is 56. So the more syllables there are, the more difficulty we have in remembering. They also looked at languages that even have more syllables than English, and it showed that they were even slower at remembering those because we process those as words in our minds, not as numbers. By age 2.5, most children can differentiate that a number is a different type of adjective. They understand the difference between a yellow dog and 2 dogs. Another interesting thing, we've talked about 1, 2, and 3 already, but these actually appear twice as much in print, the digits themselves, so not just the number 1, 2, and 3, so the leading digit on addresses. Any numbers that are used in books, the leading digits, 1, 2, and 3, are used twice as often as all the rest of the digits 4 through 9. So we have more exposure to those digits, and probably because our brains have an easier time processing them. The interesting fact, though, is smaller numerosities are any more present than larger ones. But what we do is we say, okay, we have 52 cards. That's a big number, so we're going to make it into one deck. And that's easier for us to process. All right, so now we'll talk about the actual brain itself. So a lot of what we've learned about which parts of the brains process math and which don't come from looking at patients who have cerebral lesions and also what they call split brains, so where they had to sever that bundle of nerves between the left and the right brain, usually due to seizure. And so the left and the right parts of the brain can't communicate with each other. So what they notice is that brain damage confined to cerebral areas involved in language or number can alter only a very small, a very narrow domain of competence. So if you have a cerebral lesion, it doesn't mean all of your mathematical abilities are gone, just some of them. They also found that quantitative abilities and the ability to do arithmetic involving symbol manipulation are on partially separate cerebral systems. So they looked at a few cases where they had cerebral lesions, and so they had some mathematical abilities but not others, and one of those was quantitative. So if you look at 5 plus 7, which is close to 12, they could say, okay, that's right. Even though it's not right, it's within the ballpark, but they thought it was right. Once they were given 5 plus 7 is 10, they said, well, that can't be right, that's wrong, that's incorrect. Same thing with 4 plus 5 equals 3, that's wrong. But once they were given 14 plus 25, they said that was correct. So they maintained some of that quantitative reasoning while losing the ability to actually calculate, to compute 14 plus 15. But they could understand about where the number should lie. So some of that innate quantitative reasoning we were talking about before. Both sides of the brain, so they tested in the split brain cases, they tested both sides of the brain. could understand that the number 3 and then 3 dots represent the same thing. They could match those up. They also had, each part of the brain has a procedure for being able to compare numbers. However, comparison in the right part of the brain is slower and less accurate than when they tested the left side of the brain. So both of them had an ability to compare, but it was less efficient in the right side. They also found that the right appears to be unable to identify written numbers or do mental arithmetic. So the right side of your brain can't do any of that. And also, the right side of your brain can only recognize simple Arabic numerals. So anything that becomes more complex, when they tested these patients, they couldn't identify what the numbers were once they started getting really large. However, the left side recognizes both the numerals and the spelled out words. So after doing some imaging, and they're still learning so much, one of the main places in the brain here, the inferior parietal lobe, is where they believe most of the mathematics magic happens. There's some places in the right hemisphere and there's some places in the left, but most of it occurs in this area. But even within that area, different parts work for, they believe that there's different neurons that fire during different mathematical processes. And so the brain is so complex that they haven't narrowed it down, and they don't think they're going to be able to narrow it down to very one specific part in the brain because everything's kind of working together. But they have narrowed down some places. What they also found is that word and number identification rests on different circuits. So someone could be unable to recognize words, but they could still recognize numerals. So although a lot of times if you have someone who has a cerebral lesion or some kind of injury, those two things tend to deteriorate simultaneously. It doesn't always happen. So they had a case of a woman, actually 2 women. So the first one, she would say 5 times 2 is 13 in words, but using the symbols, she never failed to write the incorrect answer. She always got it right. She knew that she could write 5 times 2 is 10, but she couldn't say it. Also, they had a subject who couldn't even write her own name. It was completely illegible, and she couldn't write words. It just looked like a bunch of scribbles. But she could solve 3-digit times 3-digit multiplication problems in neat, legible handwriting and get the correct answer. So there is a strong connection between words and numbers, but they don't necessarily lie in exactly the same parts of the brain. So while words can be impaired, numbers don't necessarily have to be, and vice versa. So currently what they're doing is they're using an fMRI to try to delve even deeper to see what's going on in the brain, what parts of the brain are working for this, what parts of the brain are working when we do this. They found that in both hemispheres, the region that we were just looking at the picture of fires only when presented with numbers. So what they did is they had a stream of things going by for people to read. They had letters, they had colors, and they had numbers. And those neurons only fired when numbers were presented, not for colors and not for letters. They believe that there's a narrow strip in between both those, in both of the hemispheres, that make a special contribution to number processing, and that different areas are more active for computation than approximation. So like we were talking about before, where young children can have this understanding of quantity and they might not be able to compute, that's actually going on in our brain as well. Part of our brain is being used when we're approximating, when we're estimating, understanding just general quantities, and then when we're actually doing computations, that's a different part of our brain that's being activated. And again, tying into verbal memory, because when we say 5 plus 4 equals 9, we're using words in our mind. So what does this mean about education? How does this affect how we teach math? So a couple of things. Again, we talked about Piaget early on, and we said a lot of things in education, currently the way that we do things still, are based on his idea that young children have absolutely no concept of number. They have no concept of any kind of mathematical computation. So there's this wait and see policy. We're not going to introduce anything too early because we don't want to damage their brains, or we don't want to, scar them. Children aren't ready to learn any math before 6 or 7. Arithmetic is best learned by rote memory. You just have to memorize it. And it's best if we start teaching logic and the ordering of sets, because you have to understand that before you can understand the concept of number. But like we talked about earlier on, a lot of this is not true. An understanding of numbers requires one to piece a mental model that provides for intuitive understanding. So when we start talking about negative numbers, we have to be able to give students a mental model that makes sense to them, that they can draw on when they're learning. So temperatures below 0, borrowing money, even extending the number line to the left. They need some kind of mental model that they can access when they're thinking about working with negative numbers. Also, during the preschool years, there's this shift from intuitive understanding of numbers to rote learning, and a lot of those intuitions that we talked about, where they can learn how to count on their fingers and add and subtract and understand quantities, a lot of that intuition is lost once we make this switch to simply rote learning. Another interesting thing is the way in which we present multiplication tables to students. Once students learn to start multiplying, we start by times 2. Okay, so this week you're going to learn 1 times 2, 2 times 2, 3 times 2. And then next week we're going to do times 3. And then you're going to keep going, but we're still going to keep reviewing times 2 and times 3. So they actually are drilled more extensively on the smaller numbers than they are on the larger numbers. They have a lot more practice with 2 and 3 than they do with 7, 8, and 9, just by the way that we present them. Also, because of the way that our minds work, once children are learning multiplication, the time it takes them to solve an addition problem actually increases. And the reason is we have something called associative memory. So when we learn 2 times 3, we also associate that in our minds with 2 plus 3. So a lot of the mistakes that students make when they're learning to add and multiply is never anything like, 2 plus 3 is 17. They don't make those mistakes, but you might get 2 plus 3 is 6, or 2 times 3 is 5, because they're so closely associated in our minds. So we don't get these gross errors, but we get these errors that are a confusion, not necessarily even a confusion, but just the way our brain is accessing that information. So one interesting thing, we talked about earlier how Chinese are better at multiplication, partly because it's fewer syllables, but also they don't learn the multiplication tables like we do, where you go through each number. They are automatically taught to reorder with the smaller digit first. So instead of learning 9 times 8, they're told, don't do it that way, just switch the 8 and the 9 and do 8 times 9. So that commutative property. And so this means they have almost half as many multiplication facts that they have to memorize. So they have less to recall in their minds. Okay, algorithms and errors. So once you get into first grade, second grade, you're learning addition, subtraction facts, multiplication facts. Time is of the essence. How many of you had the timed multiplication tables? You had 1 minute, and you had to get as many correct as you could. So at this point, our brain, in order to calculate that quickly, we have to ignore why we're doing what we're doing. We have to not pay any attention to why are we carrying the 1 or why are we doing this, because we don't have time to do that when we're trying to compute quickly. Also, the prefrontal cortex in the brain matures slowly, so that makes children and adolescents more prone to impulsiveness, to just shouting out a number answer, to saying 2 plus 3 is 6, than stopping to think. Also because they've been taught that the quicker you answer something, the more right it is. So they did a study between 6 and 9-year-olds, and they gave them this simple problem, 5 plus 3 minus 3. The 6-year-olds answered more quickly. They noticed that the 3 and the 3 would cancel each other out, and they said 5. While the 9-year-olds went through and performed the calculations step by step. They went through and they said 5 plus 3 is 8 minus 3 is 5. So the way in which they've been learning took away that intuition. They knew I have to follow the order. And so instead of looking for things that made sense, like these are going to cancel each other out, they said, oh, I have to do the addition and then I have to do the subtraction. Also, we talked about finger counting and how a lot of children learn how to do that. And I will say, even in my son's first grade class this year, they're not allowed to use their fingers anymore. When we went into parent-teacher conference, she said, we don't want to see them using their fingers. They need to just know this. But that's so intuitive, and it helps them understand it. And so we're taking away these important strategies, which actually help them understand base 10, and we're saying, nope, you just have to know it. We also frown upon using strategies when rote memory fails. You just need to know that 6 plus 7 is 13, and you have to answer it quickly. Instead of saying, okay, you couldn't remember that 6 plus 7 is 13, but in your mind you said, okay, 6 plus 6 is 12, and 7 is one more, so it must be 13. Well, that took you too long, so you didn't know it well enough. Okay? So we're taking away these strategies that we even use as adults. When we can't remember things, we use these strategies, but we're telling children it's not okay. You just have to know it. We talked about mental models and how we automatically associate them in our mind. So it's important that we ground these concepts on concrete situations versus abstract concepts, and that we give students a rich repertoire of models to draw on. So talking about fractions, giving them images of fractions or working with actual physical fractions to give them a mental model so that they can know in their mind 1/2 and 1/3 isn't going to equal a whole, because I can see the half and I can see the third, and I know that that's not going to make one whole. They did a study with immigrant, low-income, inner-city children who were behind their classmates. I want to say that these were first, second graders. All they did was they had them have 40 20-minute sessions where they just played a board game that asked them to count the number of spaces and then, using subtraction, figure out how many they were from the end goal. The next year when they tested them, these students outranked their classmates, even those who had a better initial command of arithmetic, by simply playing a board game and getting that concrete practice with addition and subtraction. So one question that often comes up is, what is the role of calculators? We can all agree that having to pull out your calculator to do 2 times 3 is very inefficient. Okay, once you get into more complex problems, to be able to have to go and get your calculator and type in 2 times 3, everything is going to be labor intensive. However, the suggestion is that while students need to know those basic facts, calculators can allow them practice with a great number of multiplication, addition, and subtraction, and not necessarily to get an answer, but to notice patterns, to notice trends, to help develop that number sense. Okay, anytime I add I add a 2-digit number to a 3-digit number. It's always a 3-digit number or larger, noticing those patterns there. Instead of having to go through and worry about getting the addition correct, let's see what happens. What happens when we multiply by a 3-digit number versus what happens when we multiply by a 4-digit number? Looking at how the answers relate to the initial problem. And so building number sense by just increasing the amount of exposure that they have to different mathematical problems. So, questions?
Seems like we're on the wrong path compared to other nations that are teaching it differently.
Right, and yeah, and I had never even heard the multiplication thing, and when I heard that, I thought, oh my gosh, that makes so much sense. And I'm glad my son hasn't learned multiplication, because that's what I'm going to do when I work on it with him. That's how I'm going to teach it. It just makes a lot more sense. Yeah. And they even noticed in some of these studies that once children could count, you know how they were doing if it was 2 plus 4, they learned to say, okay, well, I'm going to start with the bigger number 4, and then I'm just going to add 2. So they had an innate understanding of the commutative property that they could do that. But for some reason, we insist that they learned the multiplication tables 1 through 9 in that order. I've thought about it, especially with my 095 students, and using the calculator to expose them and look for patterns, because that is mostly what I find to be lacking, is that number sense. Does this answer even make sense to you? And so I haven't done it yet, but I've thought about it. Dominic.
So you're teaching a new math concept, and the student is absorbing that. Does everything go to the same part of the brain?
No. There's a different part for just general number sense understanding. There's a different part when we're associating it with words, and also when we're doing calculations. And so they haven't been able to say, okay, if you're doing addition, it's right here. And if you're doing multiplication, it's this exact spot. Because it's so complex, they're narrowing it down, but they haven't narrowed it down that far yet.
Is it ever too late to gain number sense?
No.
Okay.
And actually, in some of the studies I read, they gave kind of like a formula to follow to work on number sense and also to build memory.
Okay. So if I'm really crummy at this, I can get better?
Yes. Yep.
It seems like language gets in the way, because you talked about 7, well, that's 2. Mm-hmm. And then 1 past 10 is 11, that's 3 syllables. It's like, who came up with that? And everything through the teens is so convoluted,
right,
compared to other things. Has anybody given you thought to just saying, okay, when you get to 10, it's actually 1D, and then 1D1, 1D2, 1D3,
right,
for 11, 12, 13.
Yeah. Or just, modify the English language.
Yeah. Teach little kids that and say, this is math language, and then maybe by the time they're in 2nd grade or kindergarten,
or even just shortening it.
Make the switch.
Yeah, even just shortening it in your mind. Instead of in your mind saying 5 times 7 is 35, what if you just said, what did I just say? 5, 7, 35. Okay. What if you just said 5, 7, 35? And now you've cut out a lot of syllables. I don't know. I'll test it out on my kid.
My daughter started this.
I was so torn. No, because I understand why it is helpful and it is useful to be able to know those things quickly. But at the same time, if that's what he needs to do to get the right answer, that is what's most important. And I think our shift in those early elementary years gets away from that. It's not if you get the right answer, it's how quickly you get the right answer. And that just puts an enormous amount of stress on children as well. So it's no wonder that so many have math anxiety by the time they get out of early elementary school, because we're saying, you have to do it this exact way, instead of saying, okay, if you want to do it that way, that's great. If you don't know 6 plus 7 is 13, but you can figure it out using 6 and 6 and then adding 1, that's fine. But we emphasize a specific algorithm. You have to know this algorithm and you have to get the right answer in 15 seconds, or it's just considered a failure, when maybe our goal should be get the right answer in the way that makes the most sense in your mind.
I'm just curious, have you seen any research on the idea of letting little kids just invent their own names for some of these things?
I
Maybe
haven't.
beyond, I mean, because they probably all know 1, 2, 3, 4 if they're English.
Right.
But if they get larger numbers, play with these, come up,
Right, I haven't, but I'd
call this.
be interested to see if there is some research out there. Because I'm sure, I mean, some of the things that they've tested students on, and a lot of the research, they haven't done a lot in schools based on some of these things that they found. And so that's kind of the next step. Once they got these ideas and they tested them and they found them to be true, now they're working on applying them in the classroom and making that kind of their next area of research.
Do you know if there's any research and study done when students are first exposed to irrational numbers, getting a number sense for what that means or where they should be on the number line? That would come along later.
Right. And so they didn't, the research that I looked at, they didn't specifically, say, okay, when you're talking about imaginary numbers, but what they did say is if they have good number sense, by the time they get to those concepts and you can kind of give them something concrete to tie it into, then that will help them to better learn it.
One of your slides said something about intuition is lost in preschool years, mathematical intuition is lost in preschool years, and yet it's pretty clear from what you started with that it seems that very young children, babies, have some sort of intuitive mathematical sense. So why does it get lost?
Because the emphasis is on calculation and how quickly we do it.
Okay, I really get that, like first, second grade, but we're talking preschool, we're talking 3, 4-year-olds who are already losing that, and I don't think there's a lot of drill and kill at that age.
Right, and that's where it starts. So it's more prevalent when students get older versus very young. But if you think about just in preschool, we're learning our shapes, and you have to be able to just look at the shape and identify it. You have to be able to just look at the colors and identify. We're already starting some of those things there. You just have to look at this and know that it's 2 without tying that into a quantity and making that association.
There's so much, I got a lot of questions I'm not going to ask.
No, and it was so hard for me to narrow down because there's so much research and there's so many interesting things they found. I mean, I could have talked for 30 minutes on just studies they did with animals and having some innate number sense. And so once you get into humans and children and adults, there's just so much information out there. There's so many studies that they've done. It's really, really fascinating. But the important thing is, are we going to be able to take these things that they're finding and translate them so that we can help everybody build better number sense, that our students can have less math anxiety and a better understanding of what it is that they're doing when they're performing these calculations, because that's really essentially what gets lost.
That just triggered something. One thing you didn't mention, or not very much, and I wonder if it came up in this, is the idea of manipulatives.
Yes.
And where that fits in with all this.
Yep, and so that's something that the research didn't mention a lot, but when they're talking about these concrete mathematical models, that's something that's always brought up, is using manipulatives, using the base 10 blocks, using, the fraction pieces, so that when they're going through and they're doing these problems, they have a concrete model to tie it into, not just some abstract idea of what a fraction is. They can picture that in their minds. Any other questions?
There may be many more. I don't want to go on there. Thank you so much.
Thanks.